Alright, so I wanted to spend some time talking about these mass ejections and flares, because they are the main drivers of space weather. So here is an example of coronal mass ejection. You see this large loop contains also somewhat increased density of coronal material, and this is the Earth for comparison. Okay, and as these bubbles move away from the sun, they also get bigger. Yes, the comparison is ridiculous, but well, they're just huge. Okay? And I'll show you a few movies. So this is a movie that is. These are basically. This is the sun and extreme ultraviolet. You see some activity here, flaring activity, and right after that, you see the huge loop going away from the sun. Here is the size of the Earth for comparison. So notice this snow. Yeah. You know what this is? These are the high energy particles that are produced. Yeah. So when the bubble takes off, it drives a shock wave. Several particles, and eventually these protons hit your CCD camera.
The particles must be slower than the light, right?
Hmm?
The particles must be slower than the light.
Just a little bit.
It takes some time because when the CME takes off, it doesn't become supersonic right away. It takes some time to get the sonic barrier, and then once you form the shock wave, then the particles will be accelerated, and it takes about 20 minutes. So there will be some time lag between the peak of the X-rays coming from the flares and the flux of protons. So the protons usually come 20 to 40 minutes after the peak X-ray flux coming from the flare itself.
Where does that picture come from? A satellite or?
This is a satellite. This is a so-called Transition Region Analyzer in Coronal Explorer. So this is a satellite that monitors the sun 24/7.